So we're going to now move our focus from the ocean to the atmosphere, now with a plenary talk by Professor Schiro on atmospheric observing needs over the tropical Pacific. So take it away, Kathleen.
Thanks, Jim. Hi, everyone. It's so great to be a part of this workshop. So I figured I would start by simply outlining the major knowledge gaps, which we are all quite familiar with, at least at these larger scales. And common theme among all of these talks and discussions is these multi-scale interactions from the atmosphere side between clouds, convection, and precipitation, and atmospheric and oceanic variability. And a couple of things that also reach across scales that are major knowledge gaps that hopefully we can start addressing from combining both spaceborne and field campaign and hopefully longer term observational sites is understanding the upscale growth of deep convection, both at the mesoscale convective system level and at the scale of the MJO, and how those scales interact. And then interaction between deep convection and its environment at subdaily scales, which all of these process level studies, especially those that are touching on deep convection and its environment at subdaily scales, are really imperative for improving modeling of deep convection in global models and in really understanding, looking across scales, the impact of these smaller scale processes on model biases. And so I'll start, if I may, by framing the discussion with a key relationship that's underpinning these multi-scale interactions, which is this relation between column integrated water vapor and precipitation. And so this is known to be acting on multiple scales, and this is shown at the daily scale. I'll show a number of examples at the subdaily scale, but we've really been able to improve our understanding significantly of the coupling between the thermodynamic environment and precipitation using these bulk metrics like column water vapor, because they're easy to retrieve, both from, for instance, radiosondes, but also microwave radiometers from space, and also using GPS radio occultation. The problem comes in when we try and resolve vertically the variability in the moisture structure and temperature structure of the atmosphere. And so to just briefly kind of glance over a number of different processes, but one mechanistic explanation for this relationship is simply that when you have greater moisture in the lower troposphere, both the boundary layer and the lower free troposphere, this ends up resulting in increased buoyancy of entraining convective updrafts. And that's what's shown here on the right, where you have I've composited buoyancy profiles, hotter colors or higher column water vapor, bluer colors or lower column water vapor, and similar case for both land and ocean regions, where when you have increased column moisture and you have increased moisture in both the lower free troposphere and boundary layer, you have increased buoyancy for convective updrafts, entraining convective updrafts in particular. And this, we have found that this relationship seems to be rather universal over land versus ocean, for MCSs and non-MCSs, nighttime versus daytime, despite the fact that there are very known and distinct differences in convection between land and ocean. It seems that for a given amount of moisture in the atmosphere, a particular precipitation intensity on average can be observed. And so this is great. This has been, in my totally biased opinion, great progress for understanding controls on precipitation and precipitation predictability, but it's not at all the whole story. And in fact, there's a lot missing here. So maybe we're improving our understanding of precipitation processes and coupling to the thermodynamic environment, but there are so many other aspects of this relationship that need to be understood in order for instance, our understanding of model biases. And so for instance, this is a really nice figure from Scott Powell showing that there's a really large spread in rain rates, for instance, at high column relative humidity. And so this, I think, really nicely illustrates that high column moisture is a necessary but totally insufficient condition to trigger and sustain intense precipitation. And what's missing here is information about the convective life cycle, boundary layer versus lower free tropospheric influence on convection, many critical feedbacks, including cloud radiation interactions, cold pool interactions, surface fluxes, how the boundary layer and lower free troposphere are becoming moist to begin with, and how that moisture variability is playing a role. And of course, we're trying to think of this not only from the perspective of how is, what are the thermodynamic controls on convection and dynamic controls on convection, but then how does convection modify the environment? It's a two-way interaction. And so this is an example showing the column water vapor precipitation relation. This left panel is the precipitation rate, and on the right panel here on the y-axis, this is the probability of precipitation. The precipitation or the observations is in gray from TRIM. And you can see that actually some climate models, they do still struggle to simulate realistic sensitivity of deep convection and precipitation to column moisture, but many are consistent with this observed nonlinear strong increase in precipitation with column water vapor. So models are becoming more sensitive as we make improvements to moisture. And I think that's a very promising result. And in fact, those that are more sensitive, this is just a nod to explaining that, this is a relationship that is important across scales, is that models that are more sensitive to lower tropospheric moisture and have more realistic mean state moisture gradients end up better simulating MJO propagation, et cetera. And so I think that this progress is really promising, that models are, you can see there's some divergence at high column water vapor, but there is sensitivity in these models to moisture that's realistic, but there's a lot going on at high column water vapor, and there's a lot of spread in understanding what controls deep convection, which is going to be different across these models because they're parameterized differently, because our process level understanding of deep convection and its interaction with the environment is limited. So, reading what I have down here, diagnosing differences in precipitation among models at high column water vapor really does require an understanding of complex feedbacks and processes. And so, there are many ways that we have been observing the thermodynamic environment. They're each limited and pretty severely limited for these process level studies. So my number one, if I were to list one key observational challenge, I think is really to better sample the thermodynamic environment at sufficiently high resolution, because the thermodynamic environment and its sampling and its coupling to convection is really underpinning these critical processes and feedbacks that we need to better understand in order to improve our understanding of convective life cycles and upscale growth, and particularly in the boundary layer. So we have polar orbiting satellites that are, for instance, we're retrieving IR profiles that you can observe through clouds. We have geostation, we have GNSS that is has all-weather capabilities, but does bad in the boundary layer. We have radiosondes that are really only launched over land and sparse sampling, and then ground-based receivers like microwave radiometers, even LiDAR, et cetera. So there are different technologies, and they're all quite limited. And so it's about how do we, in a novel way, bring all of these platforms together to try and bridge these gaps, and if there are still outstanding gaps, how do we fill them? For instance, one of my suggestions at the end will be a long-term observational site. And just to outline critical processes, we have cold pools, surface fluxes, vertical velocity, mass flux, and entrainment, cloud radiation interactions, cloud microphysics. All of these critical processes, I argue, are tied really intimately to our understanding of the coupling with the thermodynamic environment. And so that puts my recommendation for improving observational observations in the atmosphere and understanding of these thermodynamic deep convection coupling kind of as number one, underpinning all of those relationships. And so this is a really nice example from Brandon Moulding. He has been doing a lot of nice work looking at convective life cycles, and I think it's a really nice way of showing, for instance, we don't have continuous sampling of the thermodynamic environment. So a lot of us, and I'm very guilty of this as well, have often resorted to reanalysis for looking at process level studies of convection. And this is something that is quite limited. So what he did was he took radiosondes from the IGRA sounding network and compared that to era interim thermodynamics, compositing over the convective life cycle, which is something I want to kind of emphasize is a new novel approach that I think we should all be kind of considering and moving towards. But anyway, so when doing this, he found, and this really nicely underscores the point that the soundings they're really sensitive in terms of there's a lot of variability in the humidity and temperature, especially in the boundary layer that's not at all being captured in era interim. So in the left, this is if you just look at specific humidity for the time being, in the interest of time, you can see that these differences in the increase in specific humidity that you see before phase 0 is the most active phase of convection. And you can see that variability, that increase in specific humidity, that's probably quite critical to convection onset and the life cycle in terms of, you can see that, for instance, the moisture decreases significantly and there's significant cooling in the boundary layer that's observed in the radiosondes. It's not observed in era 5. And so this really kind of emphasizes that we have these great data sets that in fact are quite limited, meaning radiosondes, and era 5 and reanalysis in many ways is not giving us the information that we need for, in particular, the boundary layer for these process level studies. Another thing I want to kind of, so now I'm trying to do a little bit of forward thinking and forward looking and highlighting some studies that I really think are advancing our understanding of convection and thermodynamic coupling and how we can use existing technologies to really move forward. And so we know, for instance, that mesoscale convective systems, these 100-kilometer or greater scale systems, account for 50% or more of tropical precipitation. The MCS we have this now great database thanks to Zhifeng and some others who have been working on mesoscale convective tracking databases from space that really can help us with the correct measurements, for instance, of the thermodynamic environment, and co-locating a number of different data sets, both spaceborne and on the ground and from field campaigns. Sampling across this convective life cycle is now something that we're capable of doing thanks to novel techniques and analysis of satellite-based IR, for instance, and GPM precipitation radar. However, what's still missing to advance our understanding, looking across and using these data sets, are these reliable, high-resolution, all-weather sampling of the thermodynamic environment. And MCSs are kind of thought to be potentially, they're not well represented in climate models. In fact, really, they're not represented at all in terms of memory and propagation, yet they're responsible for 50% or more in certain regions, up to 90% in certain regions of all precipitation that falls in the tropics. And so if we start to understand the processes, the critical processes like cold pools, et cetera, that are responsible and really important for mesoscale convective system organization and lifetime, if we get those right in models, is this key to reducing longstanding precipitation biases? And this is nice work from Zhifeng that I'd like to highlight that just shows that in the top E3SM, for instance, at lower resolution, you have a lot of bias in terms of the number of MCSs that are being simulated. But when you go down to 3 kilometers, you actually have much smaller biases. And so resolution certainly matters, but it's a matter also of trying to figure out how are critical processes represented, and are they represented for the right reasons? And in order to do that, in order to improve parameterization, we need multi-scale, multi-platform observations. So critical are cold pools. This is another really novel technique and new approach that I wanted to highlight because I think that the availability of satellite observations now is something that we didn't necessarily have in previous field campaigns that we can now couple to atmospheric observing systems on the ground. For instance, turbulent flux measurements that are, we cannot observe from space. So a buoy data is invaluable for that. And also critical processes like understanding vertical velocity and entrainment. We now have radar wind profilers that we have used in different ways to understand mass flux and infer properties of entrainment that are sort of new techniques that I'd like to sort of encourage us to think about using moving forward. So to summarize, I think number one, our key observational challenge is the thermodynamic environment to understand these critical processes. We have a number of existing technologies that have been helpful in past campaigns, and I'll kind of just leave them here, radiosondes, radars, et cetera. But what I think we really need to think about is we have all this satellite data, we have all these field campaign observations, and we often use modeling to kind of do these process studies in between to fill in the gaps, like understanding vertical velocity and things that are really impossible or have been really difficult to measure, cold pools. But I'd also like to advocate for continuous long-term measurement sites. There's a lot that we can bridge, I think, and learn from just setting up really long-term sites. And that we won't necessarily be able to get from short field campaigns or satellite observations. But this is all up for discussion for later. To conclude, no single platform will ever be sufficient. So, I mean, a significant challenge is how do we integrate different types of measurements in novel ways to support convection process studies like mesoscale convective tracking, cold pool tracking, et cetera. Thanks.
All right. Well done, Kathleen. I have a couple of questions that I think we can fit in before the break. The first is from Anish. So he says, could you briefly comment on how to constrain the stochastic variability in the relationship between precipitation and column water vapor versus the deterministic component? I'll stop there and see if you could.
I don't know that I can answer that well. And if I could, I would, yeah, that's a great question. I think that there's a lot we've done just by boiling things down to basics. But I don't have a good answer to that, Anish. That's an amazing question.
Yeah, I couldn't have answered it, that's for sure. I do have one more from Simon DeZoika. I think we can stop here. Are there significant advancement in techniques for understanding / separating the sampling of the convective thermodynamic environment resolution from the effects of the convection itself? Does that make sense?
Yeah, no, that's a great question. It's a really great question. Other than making sure we have continuous measurements so we can lead lag and try and understand what came first. No, not really. And a lot of these compositing studies, for instance, we try and do that. But also, if you're sampling 6 hours before a convective system came through, it's not to say that there wasn't one immediately prior to that as well that influenced the environment, that influenced the convection. And in many ways, it kind of going off of that example, it doesn't necessarily matter what happened beforehand if the environment that you've sampled is supportive of convection. So there's some sort of workaround or things to think about in terms of thinking through sampling. But other than continuously sampling, that's the question.
And I'll close it with just saying I'm a huge fan. That was a great talk, first and foremost, but I am a huge fan of continuous measurements. I consider them continuous process studies because you learn so much from having an annual cycle. You just can't beat it. I know there's other things you need to mix in, but man, I'm a huge fan, so I agree with you there.